How does it make water wetter, you ask? Good question. See, water seems to have a kind of skin. Look at that little bug walking on top of the water. Ray, can we get a close-up here, please? Oops, wrong pan of water. Ah, there's the little fella. Move on in, Ray. See how he just walks on the water? He's actually walking on the water's skin. You can see the little dents in the water skin around his feet.
Whoa! His little tootsies aren't even getting wet.
That's great, but we still have to answer this letter.
All in good time. That skin on top of the water is called surface tension. Soap weakens the surface tension. Look at this. Just like the bug, the basket stays on top of the water skin. Now watch what happens when I spray it with soap. The soap broke down the water skin or the surface tension. There was nothing to hold the basket up. Is that amazing?
Well,
I think yes.
Yes, but...
I know. How does making water wetter clean the dirt?
Nobody asked that.
I had never stopped it before.
Dirt. I need dirt.
Oh, I got some dirt. You know Ray, the cameraman?
Yeah.
He's trying to get a date with the makeup lady.
No.
Did I say Ray? Oh. I meant me. I'm trying to get a date with the makeup lady.
Thanks, Lester, but I need real dirt. Oh, here's Fuzzy, our official test dummy. How convenient. And look, his coat is dirty. Even more convenient. Why don't I clean up his coat?
How about the coat scope?
Bogus scope me. This is dirt on cloth. This is water on dirt on cloth. The dirt's still there because the skin of the water, the surface tension, doesn't get broken. It can't get at the pieces of dirt between the fibers and wash them away. But with the miracle of soap, the soap plus a little elbow grease, rubbing, makes the water wetter so it can get to all those nooks and crannies and hard-to-reach places. Wow, my whites have never looked whiter.
We've got to find out what this question is.
Indeed we do. Always keeping the ship on course. I like that about you. By the way, did I mention that soap not only cleans dirt, it cleans oil and grease?
By the way, did I mention that if you don't read the letter soon, you gotta pay the guy in the rat suit overtime?
Okay. Soap binds with oil and grease. It brings them together so the water, wetter than ever, can wash it all away. Let me show you how that works.
Beekman, the letter is still waiting. Waiting.
All right, I can take a hint. Oh, bing, bam, boom. Let's read the letter.
What's it say?
Oh, it's from Max Gordon of Fredericksburg, Virginia, and Max asks, how does soap work? Whoa, Max, I'm glad you asked. This is a fascinating topic. You see, soap actually makes water wetter. And by doing so,
wetter water. Come on, here we go. One,
which enables it to then remove water.
Coming up next, how to train your cans to come to you and roll over. And believe me, you can with Beekman. Don't go away. Get ready. It's time to broaden our brain. Here he is, the Colossus of Clarity, the Tribute of Trivia, Pet Cat. What's that? The one, the only, the Beekman.
You buy them, I'll fry them. Let me have them.
Question, dear Beekman, do birds sweat?
No, they have a unique cooling system.
I've seen a bird sweat.
What bird did you see sweat?
Larry Bird.
Speaking of birds, did you know that woodpeckers use their beaks as ice picks in the winter?
What do they use it for in the summer? A can opener?
Don't be ridiculous. They use it for a corkscrew.
Those woodpeckers really are amazing birds.
Yo-ho, Beekman, over here. We use our beaks as ice picks all year long.
Hey ho, shh, not too loud.
Why not?
Well, if the word gets out, you'll be known as an ice pecker.
Ice pecker.
Question. Nicolette Ulrich of Spartanburg, South Carolina asks, how many shots can a skunk get off before it has to reload?
2 3-pointers and a layup.
I didn't know skunks play basketball.
They don't. I think what Nicolette wants to know is how much of that smelly stuff can a skunk squirt before it has to store up again for its next shot. The real answer is enough for 6 squirts. And believe me, those are 6 shots you don't want to block.
Question. Do aircraft carriers get good gas mileage?
Are we talking highway or city? Actually, they go about 6 inches per gallon. But of course,
Your mileage may vary, sir!
on the other hand, a monarch butterfly can go 620 miles without eating. It gets a lot better mileage than an aircraft carrier.
Yeah, but try landing a fighter plane on a monarch butterfly.
Speaking of monarchs, did you know that the emperor penguin can't fly, doesn't sing, and won't build a nest? The only thing bird-like about it is its feathers.
Guess what, Don?
What?
I think we're royalty.
How do you figure?
Well, can you fly?
Nope.
Can you sing? Can you build a nest?
I'm not even gonna try.
But you got feathers?
Sure do.
Then you, my friend, are an emperor.
Ooh, what do I rule?
The remote control. But leave it on Beekman.
Okay.
Here's a frontier in imagery. This is an outline of a supersonic airplane, but not a real one. It's a mathematical model of a plane that was fed into a computer along with the calculated stresses on the surfaces indicated by the various colors. With the computer controls, the model can be rotated and flexed to see what happens to the stress. The changing colors give the designers of the plane an indication of how it should be engineered to withstand the forces encountered when it's flying faster than the speed of sound. Graduate students prepared the mathematical model and fed it into the computer as part of their work in the Computer Engineering and Science Department at the Case Institute of Technology in Cleveland, Ohio. Experimenting with a model made up of numbers, which become images that can be manipulated and studied on a computer screen, combines mathematics and engineering in a new frontier. Lila, you know the dimensions of this piece of paper.
Yeah.
What are they?
11 by 8.5.
Okay. What I want you to do now is to cut a hole big enough for you to walk through in this piece of paper.
You can't do that. That's impossible. Cutting a hole in this piece of paper?
Mm-hmm.
You can't do that.
Okay, before you leave today, I think we will have a hole in a piece of paper this big enough for you to jump through.
Jump through?
Yes.
No way.
All right. First of all, just cut the biggest hole you can in this piece of paper.
Okay.
That's as big as you can make it?
Well, except for the corners.
Yeah, you could make it just a little bit bigger. Not certainly big enough for you to jump through.
No.
Okay, now, why do you think that you're having problem trying to solve this little puzzle? Here's why. Remember I said in the beginning, how big is this piece of paper?
Yeah.
That was to make you think of the dimensions of the paper. So that when I said you want to cut a hole big enough to jump through, your mind said, well, the dimensions of the paper are 8.5 by 11, therefore the hole can't be any bigger.
Yeah. That's right.
Not right. Not
No?
right. You have to make the hole bigger than that, obviously. Okay. That's
Okay.
one thing. Look at all the paper you wasted.
Well, you can't use that to make a hole.
Well, you'll have to somehow figure it out so that you can take all of the center part and make it a part of the ridge around the edge. Okay? Third thing. When I said hole, did you think of something sort of round? You could have cut something kind of round.
Round.
Okay, but a buttonhole is a hole. How would you describe a buttonhole?
Slit.
A slit. Okay. So that's what you have to do. Get your mind thinking away from this dimension of the paper, okay? Somehow get all of the paper as part of the edge around the hole and cut a series of slits. And here's what you do. Each of these black lines is a cut, including that one down there at the fold. See, that's where I folded the paper like that. Put your finger down here and trace what happens.
It's one continuous line.
Yes. And if you cut both sides out at once, you're going to have one continuous line all the way around.
Yeah.
So that's what you do. Okay, cut a series of slits. Take the scissors and first cut like that. Okay. Now cut the other side over here. Try not to cut my finger, please. Now cut the fold. Okay, now, see these two lines here?
Yeah.
Okay, cut those. Okay. I'll turn the paper around. You cut 3 more. 1, 2, 3.
Sorry.
Okay, now open it up.
That's a big hole.
Yes, certainly big enough to put around you,
Yeah.
but not big enough to jump through. Here, you want to pick it up, please? See, what you have to do, Lala, when you want to make a hole big enough to jump through, is the same idea as that you just now, cut it into a series of slits like that, but make the spaces between the slits smaller. Very, very small. The smaller you make them, the bigger the hole. In fact, here, look. I have one that I cut out exactly like you did, but I made the slits that close together. And watch the size of this hole. Would you come with me, please? Stand out there, turn around. I have put a couple of tacks on the door, and I can put one side over there, one side over here. Are you ready? Jump through my piece of paper. You're going to play an unusual safari guessing game, going to far-off places to gather the ingredients for a common food you've eaten many times. See how soon you can guess what that common food is. First, to the tropics. Most plants are grown for their fruits, leaves, or roots, but these are grown for their stalks. Presses squeeze out the juice, which is cooked into a thick brown liquid. More processing removes the rest of the water and impurities to produce the familiar white crystals that are the first ingredient of the mystery food, sugar. Next to farms that specialize in raising cows and, of course, milking them. Obviously, the next ingredient is milk. Finally, to Africa or Latin America, where this tree grows. On it are pods about the size of a cantaloupe. They're sliced open to remove the 30 to 40 beans inside. The beans are heaped into piles and allowed to ferment, a natural ripening process during which chemical changes create their characteristic flavor. Another 6 or 7 days of drying in the sun changes the color to dark brown. The beans are shipped to a factory where they will be combined with other ingredients to make the mystery food. Different varieties of beans are blended together and then roasted in ovens. The hard shells are removed, the inner part ground up to produce a rich, smooth liquid. The sugar and milk are added, and the mixture is ground over and over again until the particles are very fine. The warm mixture is poured into stainless steel forms. When cool, the final product is removed from the forms and sent to the automatic packaging equipment. Of course, by now you've identified the mystery food. the juice of the sugar cane, milk from cows, and the beans from the cacao tree have been combined to make milk chocolate. Balloon full of water, Stacy, and a quartz watch. They have something in common.
What?
Well, first of all, I've taken that quartz watch apart so that you can take it apart yourself and turn it over. But have you ever had a wind-up watch?
Yes, I have.
Okay. What makes it keep time?
Well, there's a little spring inside of it.
Mm-hmm. And there's a balance wheel that went back and forth and back and forth and back and forth. There's nothing like that on a quartz watch, is there?
No, there isn't.
Take the top and flip it over.
Okay.
Okay. Now, there's the little battery.
Yeah.
Okay. Now, what is it that makes the quartz watch work?
Piece of quartz.
The quartz, right. And there it is right there. See that little canister-like looking thing?
Yes.
Inside there is a tiny piece of quartz.
It's pretty small.
Yeah, pretty small. And the battery, which ordinarily goes here, supplies current over to this little piece of quartz. And that's how the quartz and the balloon are alike. Here, tap the balloon on the top. Tap it a little harder. Now tap it softer. See, regardless how hard you tap it, it always vibrates at the same frequency.
Yeah.
That's its natural vibrating frequency. Well, the little piece of quartz inside there has a natural vibrating frequency also when you put an electric current on it, except it's thousands of times per second.
Oh.
And that's the place of the balance wheel. Here's a puzzle for you, Michael. See, I have this brick hanging here by a stout cord from the swing. But part way up, here's a nice thin string.
Oh, just like this one.
Yes, and down at the bottom, there's another little thin string. What I want you to do is to be able to break the bottom string without breaking the top one.
Well, I don't know how.
Well, it has to do with mass and weight. First of all, what's weight?
Well, weight is when gravity pulls it down,
And you put a scale in the air and you measure how much the force of gravity is pulling. But you could take this brick up into outer space, no gravity.
Oh, so you mean like there's still mass in outer space, but there's no weight.
Right. Okay, so this brick at the present time has both mass and weight. Gravity's pulling down on it, right? But the inertia really, scientifically, the mass is determined by its inertia. Now, let's see if I can explain.
Well,
have you ever heard of that?
What's inertia?
Well, let's see. If this were in outer space, the mass of the object would be determined by how much force it takes to get it to move.
So that's what inertia is?
And that's the inertia. The inertia is the tendency of an object to stay at still if it's still until a force of some kind moves it. So as this brick is sitting here, it has both mass and weight. If you jerk quickly at the bottom string, the inertia of the brick is still going to be there, right? And you're pulling against the inertia of the brick.
So the string will break.
This string would break, right?
Yeah.
Now what if you pull slowly?
Well, then...
You'll overcome this inertia. Then gravity and inertia together...
Oh, I'll break this string.
Okay. You sure you got it now?
Yeah.
First you're going to break the bottom one by doing what?
Pulling it quickly.
To use the mass of the brick. Now then when you pull slowly, what'll happen?
This one will break.
Okay, are you ready?
Yep.
Let's test the theory. You're going to do it real quick.
Okay.
Okay.
Broke.
Just like that. Okay, now you're going to break the top one, hopefully, by pulling it slowly. There you go. Here, I'll take the string.
Okay. Slowly?
Slowly. There. So now you know the difference between mass and weight. Fighting a forest fire is a big job that may involve hundreds of men and special equipment. Even after the fire is under control, firefighters can spend days putting out isolated hotspots. At last the fire is out, but the job is only half done. You see, after a forest fire, heavy rains can lead to disaster. Water pouring down the bare hills can carry away tons of soil and rock. So, as soon as the fire is out, specialists from the U.S. Forest Service examine the area in detail. They check the roots of the grasses for signs they will sprout again. They examine the soil to see how well it can absorb water and hold together. They estimate how much ash and mud will be carried off into the streams. The information is sent to headquarters, and in a matter of days, a forest rehabilitation plan is put into action. A helicopter spreads a mixture of grass seeds and fertilizers onto the burned area. On the ground, a team spreads the seeds of plants eaten by wildlife to encourage them to return. A dead tree is positioned to act as a terrace to slow the water coming down the hill. Debris clogging streams must be cleared away. Trucks could damage the bare ground, so a helicopter becomes an aerial crane to remove heavy logs. A few months later, the burned area is on the way to recovery. So the next time you hear that a forest fire is under control, you'll know that only half the job has been done. The other half begins when the forest fire is out. Jason, here's a window, drawing of a window anyway.
Okay.
I've got it on a little stand here, a special kind of motor down here. I'm going to turn it on. I want you to look at it, but stand back here.
All right.
And look at it with one eye.
One eye?
Okay, one eye. Are you ready?
Ready.
I want you to tell me what you see.
Okay, the window is moving about half a turn to the right, then it turns around and moves half a turn to the left.
I mean, it's going back and forth.
Yeah, it's kind of oscillating.
You sure?
Yep.
Well, I won't turn the motor off or anything. I'll simply tip it so that you can see what's really happening. Look.
What? Oh, it's actually rotating around.
Yes. Now I'll turn it back up here like this, straighten it up for a second, and you look. It'll go oscillating back and forth again.
It's oscillating again. I don't...
Well, crooked yet. There.
Why is it doing that?
Well, that's because it's an optical illusion in motion. Come on up here, I'll show you.
Okay.
When you see a window like this, it's usually along the side of a building at that perspective. This front part, the long part, has got to be more closer to you than the rear part, which is smaller.
And it looks farther away.
It looks farther away. So therefore, regardless of which side you look at, that part's always going to be, by your mind, put as far away as it can from this one. So in spite of the fact that you now know it's rotating, every time you see that section back here, the small part, your mind's going to push it away, and that's what makes it vibrate or oscillate back and forth.
That's neat.
Okay, I'll try it again. Then I'm going to add something. Go ahead. Go back there and look at it with one eye.
Okay.
Is it going back and forth?
Yeah, it's oscillating again.
It's oscillating again. Okay, now I'm going to put on something that's not part of the optical illusion, and you watch what happens.
Is that just a soda straw?
That's a soda straw. What happens?
Oh, it looks like it cuts through the window.
Yes, because it continues to rotate while the window continues to appear to oscillate back and forth.
Every second time it oscillates back and forth, it kind of cuts right through.
Cuts right through the
window.
window.
Right there.
Here, come on up here now. You see, when you get up real close to it, you can see that the window is continuing to go round and round, and so is the soda straw. And it's a neat optical illusion that you often find at science museums. And here's how you can sort of do this one at home. Make out a window shape, draw it out carefully like that, put it on a rotating shaft, and it'll look like it's oscillating. Ashley, you recognize what this is?
It's an electromagnet.
How do you know?
Because I made one at home.
Well, here, use this one and tell me what you did.
Okay. First of all, I took a big iron nail, right? And then I wrapped lots of